So for this question, I'm going to give you a little bit of an explanation, and then I'm going to get into a relatively straightforward equation to use to solve it. So it says calculate delta H reaction using the enthalpy of formation information below. And in a previous question, we saw that the enthalpy of formation reaction is for the formation of 1 mole of this, this, and this. The enthalpy of formation of oxygen is 0. So if we form 3 moles of CO2, it's tripled the amount of the enthalpy of formation. It turns out, as I mentioned, you can look up these enthalpy of formations on tables. So this is the enthalpy of formation of this, this, and this. What is this reaction? Well, we have propane, which is stuff in barbecue grills, burning in the presence of oxygen, a combustion reaction, to form carbon dioxide and water, and then it's just balanced. Okay? So this is basically what we're doing. So what we're going to imagine here is that we're going to take advantage of the fact that enthalpy is a state function, meaning that it's independent of the path. If we have a mountain like this, okay, whether we hike up this side or get ropes out and scale up this side, or we take a helicopter from here to here, our change in altitude is the same. If this is 0 feet and this is 1,000 feet, our change in altitude is 1,000 feet, whether you take a helicopter, you hike up, or you rock climb up. Okay, so that's basically a state function. Enthalpy is the same thing. So what we're going to do is we're going to assume that we destroy these reactants. We're going to turn these reactants back into their elements. Said another way, if this is how much energy is released when you form propane, then 105 kilojoules per mole will be the amount consumed when you form propane from its elements. We're then going to take those elements and we're going to combine them to form carbon dioxide and water. So we're going to use the enthalpy of formations for carbon dioxide and water because we're going to turn these into the elements and then we're going to turn them back into these products. That's essentially what we're doing here. So as I promised when I first started talking, there's a relatively straightforward equation for doing this. And it is delta H naught, standard state reaction, equals the summation of N delta HF naught of the products. What this means is add up all the enthalpies of the formation of the products times N, the number of moles of each one that you have, and then subtract the summation of N of delta HF naught of the reactants, commonly referred to as products minus reactants. Okay, so this is basically what we're going to do. What this means is we're going to add up the products and we're going to add those to the negative. So instead of this being negative 105, it's going to become positive 105 of the reactants. That's all we're doing here. Okay, so let's take a look at how you actually do this. So if you look at the delta H naught of this reaction, the first product is CO2. Remember, the enthalpy of formation is for 1 mole. It is in kilojoules per mole. So we need to take that and multiply it by 3. So we want to take 3 times minus 394 kilojoules. Now you can see why that's convenient, right? We don't need to know the stoichiometric coefficients for how many CO2s would be formed in the balanced chemical equation for this forming from carbon and oxygen. This one would work out well. But for others, it wouldn't. We just always know that this is 1 mole. So if we form 3 moles, because it says we form 3 moles, we triple this. That's what this N is. We need to add that to the next one, which is 4 H2Os. Okay, so we're going to make 4 H2Os. Each H2O is minus 242 kilojoules. So that's the summation of the products, the stoichiometric coefficient times the enthalpy of formation. Now we're going to subtract out the reactants. So our first reactant is C3H8. We have one of them, so we're going to put in our negative 105 kilojoules. This negative makes this positive. Then if we look at oxygen, oxygen is an element. So elements have an enthalpy of formation of 0. It's not given on the table. Or we just going to remember elements have an enthalpy of formation of 0. So we can either do 5 times 0 or just add 0 or just not write it at all because it's 0. When we do the math, we get delta H naught for this particular reaction is negative 2,045 kilojoules. Not surprisingly, this reaction gives off quite a lot of heat energy. Okay, because this is used in barbecue grills, which are specifically used to heat up and cook food.